Welcome to section 2.4, Systems of Linear Inequalities in Two Variables. So the idea of a system is now going to be extended not just looking at equations, but at inequalities. And you'll see in the notes on page 36, a system of linear inequalities is just a set of two or more linear inequalities to be solved together, being taken simultaneously. And just as with a system of equations, a solution to a system of inequalities is any point, any ordered pair that satisfies the inequality. Some additional special terminology. A vertex point or a corner point is the point along the edge of the solution. So we'll see when we get to graphing the solutions of these that we are going to use the idea of the overlap of the graphs to find the solution to the system. So for instance, let me graph the solution set. To this inequality, or this system of inequalities. X plus y is less than or equal to 3, and x minus y is greater than or equal to 1. Okay. So the way that I like to handle these is to graph the solution to each inequality separately. So my first inequality, x plus y less than or equal to 3, we're going to handle this exactly the same way we did back in 2.3. We're going to graph x plus y equals 3, and it's going to be solid because of the nature of that inequality. So what would that look like? Well, if we move x over to the other side, another way of writing this would be y equals negative x plus 3. So we're going to have our y-intercept at a height of 3, and we're going to have a slope of negative 1. So if we put our y-intercept at 3, and we fall 1 and run 1, and we fall 1 and run 1, and we fall 1 and run 1, we can see this is the line that we're talking about. And I will use a solid line. Okay. Now our inequality is going to be is going to involve shading one side or the other of this line. We see that the line is part of the solution, but should we also shade above it or below it? Well, I will test the origin just to see. And in my original inequality, 0 plus 0 sure is less than or equal to 3, so the origin works, which means everything else below this line is a solution. Okay, so there we have our first linear inequality graphed. I'll graph my second one separately to kind of see what's going on with that one. So x minus y greater than or equal to 1. So first I'll graph the line x minus y equals 1. And if I solve for y, maybe negative y equals negative x plus 1. If I make both sides of this equation negative, or rather if I multiply both sides of this equation by a negative value, I'll get y equals x minus 1. So our setup have negative 1, 1, 2, 3, 2. And here we have a slope of 1, so if we plot our y-intercept, and again I'm going to use a solid line because this is a greater than or equal to. So if I plot my y-intercept and I rise 1 and I run 1, and I rise another one and I run another one, and so on, see that is the line of interest. So our last task is to pick a test point. Again, I can use the origin, so I will. I'll test 0, 0. And if I plug 0 minus 0 into my inequality, is 0 minus 0 greater than or equal to 1? That is false. 0 is not greater than or equal to 1. So the origin did not work, which means we'll shade on the other side of this line. So separately, I have the image of every solution to each inequality. If I put those two ideas together, and I'll do this a bit bigger than before. I'll do -1, -2, 1, 2, 3, 1, 2, 3, 1, 2, and 3. Well, that's not the right place. Put that a little further over. Okay. So what do our solution points need to do? Well, they need to be below each of these lines. So I need to figure out what is the highest point that can possibly be a solution. And a nice way of doing that would be to transcribe maybe one of these solutions onto the other. I'll transcribe the second solution onto the first solution. Here we see our y-intercept and our slope of 1. And I will stop drawing that line as soon as I get to where I'm not supposed to draw solutions anymore. So here at 2, 1, if I continue beyond the downward sloping line, that's not going to make any sense because I would now be indicating solutions that are not actually solutions to the first inequality. So, below the line that we're seeing there, the new line, we see the overlap. So below the downward sloping line and below the upward sloping line, we have this region down here. So it gets a little bit jumbled, and I usually like to make a new copy. So I would like to be below both lines, or on either one of them. So from -1, we'll slope up 1, and then slope up another 1. Now that was where we hit the downward sloping line, which slopes downward at a rate of 1 per 1. Okay, so if we connect both of these up with straight lines and shade below, now in addition to the area that we've shaded, the line segments are also part of the solution, as well as this vertex point, this corner point here at 2, 1. So that is all that we need to do in this section. Now sometimes the vertex point is not as obvious, it's not as easily picked out as it was in this case. We can visually find this intersection point because our slopes are pretty simple. In that event, if we need to find the intersection point, we can treat the situation as if it were a system of equations. We could solve for the intersection point where x plus y equals 3 and x minus y equals 1. So here we're just talking about the two lines that we see pictured, and that vertex point would be the point where they intersect. So if we use elimination, let's see, we add the bottom equation to the top equation. Our x's would give us 2x and our y's would cancel. And we would get 4, so 2x equals 4 implies that x equals 2. Then we can back substitute x equals 2 into either equation. I'll use the top one. So 2 plus y equals 3. This implies that y equals 1. And there we get our vertex point. Now, some of the systems we'll see later on have multiple vertex points, and we'll discuss that in greater detail in class. For now, I want to look at a slightly different situation. Suppose that we had a system of the form y is greater than 3x minus 2, y is less than or equal to 3x minus 5. So we can use the same approach. We'll graph each of these and then see where the overlap lies. Now our first inequality, y is greater than 3x minus 2. We could graph that by graphing y equals 3x minus 2. This time we'll use a dotted line since our inequality is strict, since it's strictly less than. So if we put our y-intercept down at -2, it'll be open. If we rise 3 and run 1, put another open circle. We could rise 3 more and run 1 more. Put another open circle, and then we'll connect these all with a dotted line. So it's a little tough to see, but I could still use the test point 0, 0 to see whether to shade above or below this line. So if I plug 0 into the original inequality, 0 for y, is that greater than 3 times 0 for x minus 2? Well, the 3 times 0 is just 0, so is 0 greater than -2? Yes, it is. So this point works, which means we will shade above the line. Okay, our second inequality, y less than or equal to 3x minus 5, we'll graph the line y equals 3x minus 5. This time using a solid line, since the inequality is non-strict, admitting that equal to is okay. Alright, so we'll plot our y-intercept at -5, and we'll rise 3 and run 1, and rise 3 more and run 1 more, and connect those using a solid line. Now again, I can test the origin since it doesn't lie on this line that we've graphed. In my original inequality, is 0 less than or equal to 3 times 0 minus 5? Well, the 3 times 0 doesn't contribute anything, so what we're really asking is 0 less than -5, and no, it is not. So that test point is not a solution, which means we need to shade on the other side of the line. So if I put these two ideas together, -1, 2, 3, 4, 5, 1, 2, 2. My dotted line had its y-intercept at -2 with a slope of 3. And we wanted to shade above. My other line had a y-intercept at -5 with a slope of 3 also. And so we would shade below that one. Now, since these lines that demarcate the solution to each inequality are parallel, and solutions to one inequality lie above one line, but below the other line, looking at this supposed solution set, I can see that there is not a single point anywhere in the xy plane satisfying both inequalities. There is no solution to this inequality, or system of inequalities. And that certainly can happen. We can pose a system where no point will satisfy both inequalities, just like back in 2.1 and 2.2 we saw that there are systems but simply have no solution when we're dealing with more basic equations. So use this strategy, graph both systems, or both linear inequalities in the system separately, or you can graph them on the same plane. It's a matter of taste. I do recommend graph paper for these types of problems as well. It will help quite a lot. Once you can see where the solutions to each inequality overlap, that overlapped area is the solution to the system, because every point in the overlap satisfies both inequalities. So go ahead and get started on those homework problems. Shoot me any questions you have via the Ask Your Teacher button. Otherwise, bring any questions you have to class and we will look at some more interesting examples there.